Over the next several videos, what I would like to do is a tour of how to write proofs in mathematics so that you feel comfortable both reading and writing proofs on your own. In this video, we are going to start by just looking at the types of statements that we set up when we do a proof in mathematics. So I will call these if-then statements. They are also called implications or conditional statements. The thing is, when you study a field of mathematics, what you usually do is establish at the beginning a set of axioms. The axioms are like universal truths that we don't prove. Every conclusion that we reach after that, as we study the consequences of our axiomatic structure, is a conditional statement which needs to be proven. So, what feels like a huge amount of facts that you might learn in something like a real analysis course are all kind of logical deductions that we move through and we prove as we dig deeper and deeper into the subject. Okay, I would like to start by just establishing some notational conventions and some language conventions. We will see lots of explicit examples of phrases in just a moment, but let me say that an if-then phrase is often presented exactly like this. If a hypothesis or a condition is being met, then a conclusion will follow. In my opinion, the use of the word hypothesis here is interesting because in a general scientific context, a hypothesis is often an idea or a theory that's going to be tested, perhaps experimented on. In a conditional statement in mathematics, the word hypothesis refers to an assumption that we make, and then we test if the conclusion is true. So it's like we assume this and we see if this follows. If it does, the if-then statement is a true statement, and it could be labeled something like a theorem or a proposition. If it's not true, then it's just a false statement. Typically, you would say, hey, here's a counterexample that demonstrates that this hypothesis does not necessarily lead to this conclusion. Okay, so that's going to be the language conventions that we will use as we look at proof writing in math. The hypothesis is an assumption. The conclusion is something that we want to see follows the hypothesis. And until it's proven, the entire statement you could think of as a conjecture. Let me run through some notational remarks before we actually look at statements. I will often think of the hypothesis as P, meaning I will write if P, then Q. So in shorthand, to kind of work through the logic of this type of statement, we could write this concisely as if P, then Q, meaning if some hypothesis, then a conclusion. These statements are often called implications, and we might write this statement even more concisely as P implies Q. So that's like very shorthand. So you might have a hypothesis and then just this special looking right arrow, that's the implication arrow. The hypothesis implies the conclusion. And then something that you don't see quite as much is P only if Q. Kind of have to think for a minute about why this phrase means the same thing as if P then Q. But basically, if this statement is true, it means that every time you observe P, you must also observe Q. P always leads to Q. So P only if Q is trying to say you can only have P if you have Q. Okay, so just be a little bit careful with this kind of phrasing because I think putting if in front of Q almost makes it feel like it's reversing the role of the hypothesis in the conclusion, but technically this is the same idea as this original implication. One thing I will point out as we work through examples on the next few slides is that statements in math are not always presented with this precise language of if the hypothesis, then the conclusion. So sometimes statements, and we will see examples of this, are phrased in such a way that they don't use any of this language. They're almost stated just like facts. So one thing that you want to develop is you want to read something that which looks like a fact and extract from it what's the hypothesis, what's the conclusion, and develop the ability to rewrite it in an if-then way. It seems to be tradition in logic classes to start with statements about the weather. So let's look at this pair of statements. If it is raining, then Mary has an umbrella. This statement has been given to us in the traditional if-then way. Compare that to the second statement. Mary carries an umbrella whenever it rains. What's the difference between the two if there is one? because of the way it's been phrased, the first statement is immediately a conditional statement. It's an implication, and we can identify right away that the hypothesis is that it's raining, and the conclusion is that Mary has an umbrella. So if it is raining, then Mary has an umbrella. This is what I would call P, and this is what I would call Q. In shorthand, you could write this as, say, if you were taking notes, rain implies Mary has an umbrella. For the second phrase, we don't have the word if, we don't have the word then, so we have to do a little bit more work to recognize what's going on. Mary carries an umbrella whenever it rains, which means that every time we see rain, then Mary will have her umbrella. It would never be the case that it was raining and Mary didn't have her umbrella with her. So she always has her umbrella if it is raining. That means if the rain is happening, it must follow that Mary has her umbrella with her. So the second statement is actually a rephrasing of the first one. That's the conclusion here. And I wanted to point this out just to illustrate, and we'll see more examples of this, that conditional statements are not always phrased so clearly as this one. And sometimes because it just sounds more natural. I think after we've gone through some mathematical examples, you'll see that this kind of statement can be more concise and kind of easier to remember than maybe a longer phrasing using if and then. It's also important here to notice that the order that the kind of players in this sentence was reversed from sentence 1 to 2. So Mary came first and the rain came at the end, but we needed to recognize that this is the hypothesis and this is the conclusion. So this is often the first layer when you look at a conditional statement. If it's not given to you in this form, you want to practice recognizing what the hypothesis and the conclusion are. You never want to leave a theorem without having identified the hypothesis and the conclusion, because if you don't recognize what they are, you probably don't really understand the theorem and you won't be able to prove it. So always train yourself to say, what are the hypotheses? What are the conclusions? Sometimes it's immediate. Sometimes you have to do a little bit more work. Let's now look at 5 examples of mathematical statements which are not phrased in the classic way, but they are all implications. What I would like to do for each of these is read it out loud, give you a moment to recognize the hypothesis and the conclusion, then I will come back and rewrite it as an if-then statement. So the first statement that we're going to dissect is a number is divisible by 6 if it is divisible by 2 and 3. So recognize the hypothesis and the conclusion. You can go ahead and rewrite it in the more traditional if-then way if you'd like. In this first example, we do have the word if. So we have part of the if-then phrasing that we're about to write down. And kind of like the Mary umbrella example a second ago, the hypothesis has been put at the end. It's like the conclusion is being given more emphasis here with the ordering of this sentence. But reading through this, what we want to recognize is this is the hypothesis, this is the conclusion. And if I were to rewrite this, which I'm about to do, we would say if a number is divisible by 2 and by 3. So I'm just going to write if a number is divisible by 2 and 3, comma, then it is divisible by 6. Okay. Take a second now to look at the second statement. The square root of 2 is irrational. I'm going to guess that you found sentence 2 much harder to work with than sentence 1. However, this phrase here, the square root of 2 is irrational, this is a famous statement, and it's usually phrased almost exactly like this. Looking at it, it doesn't even really feel like there are two statements or conditions that we're kind of weighing against each other, like in the examples that we've seen so far. It really feels like just a blunt statement. So if I was looking at this for the first time and I was trying to figure out what the implication was, I'd say, well, the conclusion seems to be this irrationality. It feels like that's what we're reaching with this sentence. So it's like, okay, if I've got the square root of 2, it's irrational. If something is the square root of 2, then it is irrational. And through that kind of breakdown, you start to see the hypothesis and the conclusion. Okay, So it's like if your number is the square root of 2, then your number is irrational. All right, if x equals the square root of 2, then x is irrational. Let me write that out in words, and then I'll give you a shorthand for that. Then x is irrational. By the way, if I wanted to say in shorthand that x is rational, I could say x is an element of the set of rational numbers. So this is element of, and this is the set of rational numbers. Not that. So x is irrational, and shorthand is written this way. X is not an element of the set of rational numbers. Okay, that breakdown probably prepares you a little more for sentence 3. I think actually reading through 2, 3, 4, 5, you see that they're all kind of a level beyond example 1. So take a moment to pause and work through the hypothesis and conclusion for the third example. Number 3 is challenging like number 2. So if you're not there yet, let me just give you a hint. And that is, compared with number 2, I said, what seems to be important about this statement is the fact that this number is irrational. So this seems to be like the conclusion in some way. It's like what we're getting to with statement 2. So what is so important about statement 3? What's like the key fact that we're trying to land on in statement number 3? Okay. First thing I'm going to do is erase this because it's kind of blocking me, but hopefully as you reread statement 3, the part of it that you recognized as, what feels like it should be the conclusion is the fact that there are infinitely many. So then you could almost write backwards and be like, then I know there are infinitely many. What must be the hypothesis? Well, I'm looking at prime numbers. Okay, if I'm looking at the prime numbers, then I see infinitely many of them. Okay, let's phrase this a little bit better. If S is the set of prime numbers, by set here I mean collection. So if S is the set of primes, then S is infinite. Sometimes the word infinite makes people think of the wrong type of infinity. So, I mean, like infinite length or something. Let me write, then S has infinitely many elements. My hesitation a second ago. So sometimes when you say an infinite set of numbers, people struggle to think, does she mean infinite length, infinite cardinality? But here I meant infinite cardinality. Infinitely many elements belong to this set. I think the fact that I was so weird about how I was going to phrase this conclusion kind of underscores the fact that the original phrasing is nicer, right? There are infinitely many prime numbers. This is a very natural thing to say. If S is a set of primes, then F has infinitely many elements is a lot more tedious. And that is, again, why we often see statements in math phrased in like this very concise language where it sounds like we're stating facts, but what we're really stating are results that we can then prove. Okay, example 4 is from calculus. Example 5 is from linear algebra. Whether or not you have a background in these subjects, please take a moment to try to rephrase these statements as if-then statements. Number 4 says that differentiable functions are continuous. Again, it's like we're getting to the idea of continuity. If I have a differentiable function, then I have a continuous one. So let's write if f is differentiable. I'll write diff. If f is differentiable, then f is continuous. For that, I will write CTS. Okay, let's wrap up now with example 5. Originally phrased, number 5 is the determinant of an invertible matrix is non-zero. I like this example because the hypothesis is dropped in the middle of the conclusion. So we've got a bit of the conclusion here, a bit here, and then the hypothesis right in the middle. So it's like, if I know a matrix is invertible, then I know its determinant is non-zero. So that's the implication. This is going to be tricky for me to write down here, but if, and again, I'm going to drop in some notation here, if A, so that's going to be the name of my matrix, if A is invertible, then its determinant, which we'll write as the determinant of A, is non-zero, is best written like this. There we go. Okay, so I hope you enjoyed these 5 examples. 2 through 5 are all pretty famous statements, and they're often phrased exactly this way. So I wanted to identify real statements that you will encounter in mathematics, which would be phrased most commonly as their original versions. Again, you want to practice identifying the actual implication in these statements, which just sound like facts. So what's the hypothesis? What's the conclusion? All of these statements are true. So all 5 examples here are true. However, they didn't have to be. So you can have an if-then statement which is actually false if it was the case that this statement was false. Then I would need to find a differentiable function which was not continuous. I just want to mention that right now, but let's move on to a new idea. What we're going to do now is define a new type of conditional statement. It's called the contrapositive. We will take these original statements, which you'll recognize as examples that we have already seen, and for each, we will form its contrapositive. After we've seen 4 examples of a contrapositive statement, what we will do is then talk about the significance and why you would ever want to do this. So I'll save the meaning behind the contrapositive for the end of our discussion here. Let me start by saying what contrapositive is. Remember, if P then Q is P implies Q. Take that statement and form its contrapositive. What you do is you say, not the original conclusion Q. So for that statement, negate its conclusion and form a new conditional statement by saying, not the original conclusion implies not the original hypothesis. So it's a new conditional statement. It's an if-then statement in its own right. And you get it by taking the original statement, negating both pieces, and then swapping the order. Okay. Just a couple of remarks here. Just notationally, not Q implies not P is sometimes written with a tilde symbol. So not Q implies not P. Or instead, a different kind of symbol that looks like this, not Q implies not P. All right. Let me quickly run through the first example, and then I will give you a chance to pause for examples 2, 3, and 4. So our first example is how we opened. If it is raining, then Mary has an umbrella. I want to write down a brand new if-then statement by taking the original conclusion, negating it, and saying that implies not the original hypothesis. I think it's better if we just go ahead and do this. Mary has an umbrella was the original Q. So negating that would be to say Mary does not have an umbrella. So let's start by if Mary does not have an umbrella. I have a long phrase. Then it's not the case that it is raining. So it is not raining. Okay. It's a brand new if-then statement. And hopefully you see this is the opposite, the negation of the original conclusion, and this is the negation of the original hypothesis. So if Mary does not have an umbrella, then it is not raining. The second one is a slight rewording of our statement that the square root of 2 is irrational. Take this and set up the contrapositive. All right, our original conclusion was that x was irrational. So then we want to say if x is not irrational, but a number is either irrational or it's rational. It's one or the other. So when we negate the idea that x is irrational, we can actually flip it to x is rational. So if not q for this phrase will be if x is an element of the set of rational numbers and I slightly redid the opening here, then it is not the case that x squared is 2. It is not the case that x squared is 2 is better written as x squared is not 2. There we go. All right, so the contrapositive of if x squared is 2, then x is irrational is if x is rational, then x squared is not 2. All right, try examples 3 and 4. Go ahead, do both, and then I will come back and do them together. I hope examples 3 and 4 went well for you. For example 3, there's nothing very clever about the contrapositive here. So the contrapositive of if f is differentiable, then f is continuous is just if f is not continuous, then f is not differentiable. And then for example 4, if you want to say that the determinant of A is not non-zero, then what you're saying is that it is 0. So the contrapositive is if the determinant of A is 0, then A is not invertible. Notice in examples 2 and 4, we negated something where you're either the condition or you're not. So there was like a clean way to do it. To say that you are not rational is to say that you are rational. And likewise, that you're not non-zero is to say that you are 0. So with the contrapositive, there can be like an overly wordy way sometimes, and sometimes there's a cleaner way to do it. So I encourage you to try to find the cleaner language when you recognize it. All right, let's talk now about the importance of the contrapositive. Examples 2, 3, and 4, the original statements are all true mathematical statements. What I'm going to ask you to do in a moment is pause and judge whether or not the contrapositives are true. Can you even tell? So if 2, 3, and 4, if you know these to be true, if you have a feeling for these mathematical statements, test the contrapositives. And then for sentence 1, I don't know, Mary, so I don't know if sentence 1 is true or not. Think of it both ways. So imagine if the first example was true. Could you get a feel for the truthiness or not of the contrapositive? And likewise, what if sentence 1 was false? What do you think you could say about the contrapositive? Let me jump straight to the answer, which is that if an implication is true, then so is its contrapositive, and vice versa. If the implication is false, so is its contrapositive. In other words, the original statement P implies Q and the contrapositive statement not Q implies not P, they have the same truth level. Okay, so they're either both true or they're both false. Which means that when you're looking at an implication, P implies Q, and you want to prove it, you can prove it in a way that we call direct. So a direct proof would be P implies Q. And we will talk through examples of that. I don't want to get into proof writing right now. But it would be equivalent to show the contrapositive. So if you want to prove that, say, this statement is true, and you can prove this statement instead, then you've done the necessary work. So the contrapositive, it gives you a different point of view, different way to approach proving a statement. And sometimes the contrapositive is just interesting in its own right. So it's like anytime you have a conditional statement in mathematics, you get a second conditional statement at the same time, the contrapositive. Both can be interesting, both can arise in computations, and looking at either statement and proving either statement proves the other one. So the contrapositive just gives you like a nice change in the point of view, which is got all of the same kind of truth values as the original statement. Okay, I want to look at a pair of statements now where we will talk about the contrapositive. I don't want to get too pedantic, but I just want to talk about being kind of careful with negating ideas for a moment before we look at yet another type of statement. I don't want to spend too much time on this exercise, but what I wanted to lift up for you is that you have to sometimes look at a hypothesis as having a few different layers or different assumptions that you're combining together. So sometimes a hypothesis can have multiple conditions. And when you pass to the contrapositive, you want to think carefully about what you're negating. So the statements 1 and 2 here are really saying the same thing. An odd integer squared is odd. For example, 3 squared is 9, negative 11 squared is 121. FYI, this notation here means that m belongs to, or is an element of, the set of integers. So that's what that z symbol is. So both of these are the same thing. They're just phrased a little differently. What I would like for you to do is pause and individually write contrapositives for both. You shouldn't look too much at the other one. I don't want sentence 1 to influence how you take the contrapositive of sentence 2 and vice versa, so try to do them distinctly. When we come back in just a moment, I will propose 2 contrapositives and we will assess whether or not I did it correctly. Here are 2 contrapositives. So for the first one, I left alone the statement that m is an integer. It happened before the if-then statement. And that's not unusual because often when you're learning mathematics, it's in the middle of some narrative. You might be reading a textbook or a mathematical paper and you're studying some object and then you arrive at some kind of statement about it, right? So here, imagine I'm studying integers. And then I want to say if m is odd, then m squared is odd. The contrapositive of that, if m is an integer, is if m squared is even, then m is even. Okay. On the other hand, the second statement is the contrapositive, except not actually done correctly. And that is because here I have not peeled off and separated out the condition that m is an integer. And so the negation of m squared is odd is not m squared is even, but rather not an odd integer. Then m is not an odd integer. Integer. And it matters because the first contrapositive is a true statement. The second one is not, the way that I phrased it originally. A counterexample, because I'm originally had here a false statement. A counterexample would be, say, the square root of 8 squared versus the square root of 8. So the square root of 8 squared is 8, that's even, but what you squared is not even. It's not even an integer. Okay, so this is probably going a little too far in this discussion, but sometimes your hypothesis has kind of multiple layers. Here it was that we were working with integers which were odd. It's okay sometimes to say, I'm going to fix certain conditions like this one, and then kind of like separate out the rest. All right, just be careful when you don't do that, that you negate correctly. So if I haven't done that, if I haven't peeled off the assumption that m is an integer, the negation of odd is not even, but rather not an odd integer, could be any other kind of number. Okay, I hope you got something out of this discussion. If not, it's okay. And let's move on now to another type of statement that we will look at called the converse. We saw that the contrapositive for an if P then Q statement is if not Q, then not P. The converse is another implication that you can form out of an original statement, and it's actually easier to phrase. You just reverse the order of the conclusion and the hypothesis. So the converse of P implies Q is Q implies P. Okay. No negation or anything like that. We just interchange the roles of the hypothesis and the conclusion. So let's just do these ones out loud. If it is raining, then Mary has an umbrella. What is the converse? It would be, if Mary has an umbrella, then it is raining. For the second one, if n is divisible by 2 and by 3, then n is divisible by 6. The converse would be, if n is divisible by 6, then n is divisible by 2 and by 3. The third one, if x squared is 2, then x is irrational. The converse is, if x is irrational, then x squared is 2. No, it's just, I'm going to, spoiler alert, that's false. Okay. The fourth one is, if f is continuous, then f is differentiable. And then the last one is, if the determinant of a is not 0, then a is invertible. Okay, I've already ruined one conclusion, which is that, it's not the case that the square of every irrational number is 2. But for the rest of them, take a moment just to assess whether or not they are true or false. Compare them back to whether or not the original statement was true or false so that we can reach whatever we can say here about the converse. All right, let's skip the first one because we don't have an actual Mary to assess. So starting with the second one, if n is divisible by 6, is it also divisible by 2 and 3? You may have tested that on a few numbers divisible by 6. And what you realize is yes, because 6 is 2 times 3. So this statement is true. The original statement is true, and the converse is also true. As I pointed out, the second one is not, or the second math example, the third sentence on this phrase, the converse is not true. If you want to say a statement is not true, the most efficient way to establish that is to give a counterexample. So what is a counterexample to the converse, which was if x is irrational, then x squared is 2, would be, say, x is e. E squared is not 2. Hopefully I don't have to show that to you, but e is bigger than 2, so probably believe it right away. Okay. If f is continuous, then f is differentiable. That is also false. And again, to say that it's false, the most efficient way to do that is to provide a counterexample and take, say, the absolute value function. If you're familiar with these notions, you will know that it is continuous at the origin, but it is not differentiable at the origin. And then the last one, is it the case that if you have a determinant of a matrix, which is not 0, the determinant is not 0, that the matrix is invertible? And that is actually true. So all 4 of these math statements, the original statements were true. For the converses, 2 of them were true, 2 of them were false. So unlike the contrapositive, there is no hard and fast rule about whether or not the converse will be true. However, I think it's always worth analyzing the converse because either you arrive at a true statement, like here, examples 2 and 5, in which case you have another statement, or it's useful to practice spotting counterexamples. The more you can generate counterexamples to statements, the better you understand them. So I think looking at the converse and saying, no, that can't be true. Here's a counterexample. It reinforces your knowledge. And I also think sometimes it helps you feel the other direction better as well. Statements 2 and 5 are examples of statements where P implies Q and Q implies P. This is a statement that we see sometimes that has its own name. I will show you that in just a moment. I want to wrap up this lesson by pointing out that something special happened a moment ago. We had 2 examples where the original statement was true. So we had statements of the form P implies Q, which were true. And then when we looked at the converse, we saw that the converse was also true. So Q implied P. When that happens, we say we have an if and only if statement. We sometimes use this shorthand double-sided arrow notation. I like that a lot. You often see in formal writing the phrase if and only if, which means if you have P, then you have Q, but also vice versa. If you have Q, then you have P. So you either have both or neither. And then if and only if is often abbreviated in shorthand with if with 2 F's. So that's not a misspelling. That's an abbreviation of if and only if. To prove an if and only if statement, you just have to think of it as 2 statements that need to be shown. So you have to prove P implies Q, and also you have to prove Q implies P, and we will look at examples of doing that. Okay, so I hope that you enjoyed this look at conditional statements with me. Thank you for your attention.